to this video, we'll be discussing hydraulic losses in series and parallel systems, and we'll be focusing on an example that's used in a lot of applications. It could be piping system for any fluid, or to be more specific, piping systems used in heating, ventilation, and air conditioning, HVAC systems, and that's when the fluid, such as water from the chilled water system, runs into coils. So we'll be looking into that. But before we do that example, let's look into the general explanation for the difference in head loss between series and parallel systems. So first, what do we mean by a series system? For example, if we look into this schematic here, if we have two tanks and they're connected through as we can see, a series of pipes. They have different diameters. Therefore, we have that's L1, L2, L3. So we have pipe number 1, pipe number 2 in the middle, and then pipe number 3. These pipes are connected in series. There is a quite a good analogy between electric circuits and these systems here in terms of the flow in series and parallel pipe systems. For example, if we look into an electric circuit that has a couple electric resistances, so what happens is if we have a voltage V here, it's going to drop to V2, V3, and so on, due to these resistances R1, R2, and R3. What's fixed across this is that the electric current I, it remains constant. What's happening? We have delta V here, that's delta V, let's call it A, and actually let's call these as, I prefer to use delta V1, 2, 3. So let's call these VA, B, C, and V sub D. And here we have also our E, F, and G. So here we're going to have the first voltage drop, delta V1, delta V2, and delta V3. The same way for hydraulic systems, we have the hydraulic loss for each one. So as we move, there's a drop in the pressure and a drop due to friction. We're only discussing frictional losses. So in the first one, we have head loss 1, and that's similar to the voltage drop, and then head loss 2, and in the last one, we have head loss 3. What's constant is the flow rate Q that travels through the system. So how do we, if you want to do a check to know whether your system is in series or a parallel piping system, just check the flow rate. If the flow rate splits, then it's a parallel system. If the flow rate remains the same, similar to here, the electric current, if the current is the same, one that flows through all the resistances, then it's a series system. Whereas here, the flow rate Q, it's the same that flows through these systems. We're not going to be discussing friction in tanks, mostly because we said the velocity, it moves very, very slow, and if we use Darcy's equation, so the head loss, that's what we're going to use. So it's FL over D times V squared divided by 2G. I can use the definition for Q, the flow rate Q, which is area times velocity. I can substitute that here. But before we do that, if we apply this equation for the two tanks, the velocity is very slow compared to the velocity inside the pipes. So we're not going to see a lot of losses, or there is some loss, but it's negligible compared to the losses inside the pipes. That's why when we say from point, if we're considering the loss from point A to B, that's going to be critical for the proof of the head loss in the parallel system. So if we say that, we're only going to look into the losses inside the pipes. So now if I substitute this equation back here, so this would yield into FL over D. V squared is Q squared divided by A squared. And then we have 2G. I can substitute here pi over 4D squared and then square it. So that would be D to the 5, or just leave it as is. So all that I can actually just rename this as the characteristic, if you want C, characteristic factor of the pipe. It depends on the area, it depends on the length, the diameter, and of course the friction loss. But all that should, we're gonna have it as C1. For example, if I look into the head loss from A to B here, it's equal to C1 Q squared. Again, Q is not going to change, the flow rate, plus C2 Q squared plus C3 Q squared. Or we can simply say it's actually the head loss, excuse me, the head loss in pipe 1 plus the head loss in 2, and so on. All right, let's apply this concept to a parallel system. And let's start with a point anywhere inside the tank. As we said, we're not going to look into the losses inside the tank, and let's call this point B anywhere right here. And let's apply, first let's check. I said there's a check to know if it's parallel or series. That's the flow rate going from A to B. Let's call it Q. As we can see, if that's pipe 1, 2, and 3, the flow rate is going to split into Q1, Q2, and Q3 through each pipe. So those pipes, 1, 2, and 3, they're pipes in parallel. So what's the relation of the head loss between each one of those, and how do we prove it? So let's consider Bernoulli's equation between points A and B. However, if you recall Bernoulli equation, it applies to a streamline, so it has to be either the line that goes through pipe number 1, or pipe number 2, or pipe number 3. So if we consider path number 1 through the streamline that goes through pipe number 1, it would be PA, the static pressure at A, divided by the specific weight, plus ZA, plus the velocity, A squared divided by 2G, minus the head loss. Now, which head loss? I'm gonna, as we mentioned, neglect the losses inside the tank, so I only have the loss through the pipe that I'm going through, which is head loss number 1. That's equal to PB plus VB squared, or let's just keep the same order, plus VB squared divided by 2G. Okay? If we consider now the same, but this time going through pipe number 2, those are still the same, the initial conditions at A. What would change is the head loss through the pipe, so it's minus head loss 2 equal to the same and then of course for number 3 we're going to get the same equation, except the head loss would be the one that changes. It's going to give us this time head loss 3 minus head loss 3. The only trivial solution for this system is that the head loss through pipe number 1, or H sub L1, has to be, because if you consider those two, you equate them, you're going to cancel all the terms on the left side, all the terms on the right side, and you'll be left with head loss 1 equals head loss 2 equals head loss 3, and so on. Okay, so the head loss for this pipe is equal to the head loss here, and is equal to the head loss through pipe 2. The same can be said in this example here. We're going through the same tank. This time we have a pipe, a main pipe, it's number one, and then it splits into pipe number 2 and 3. We want to prove that the head loss 2 is equal to head loss 3. So first we need to check where's the parallel system. You can say all the way from here to here, or just consider from here to here and from here to here. So pipe number 2 and pipe number 3. How do we know it's parallel? So we have the main one, Q1, the flow rate, the main flow rate. It's coming as Q1, and then it splits into Q2 through pipe number 2 and Q3 through pipe number 3. Now, if we apply again the Bernoulli equation from A to B, consider any path you want. So you will have the same, except this time we're going to have head loss 1 and head loss 2 in the first equation, head loss 1 and head loss 3 in the second equation. So of course it's minus because that's the upstream. So it's minus head loss 1, head loss 2, head loss 1, head loss 3. If you equate those two equations together, again, all these terms are going to drop. Even head loss 1, the one highlighted in yellow, would also drop because it's the same, and we would end up with head loss 2 equals head loss 3. So now for parallel systems, once you have your system set, then the head loss has to be equal. That's slightly different than the example that we're going to discuss. But that's the main concept, which is parallel systems should have the same value. So let's look into this example where we have a pump. Excuse me. We have a pump. We need to find the head for the pump and power. Before we go into more into the details and what's there, so we have 4 different pipes. That's a system used in HVAC, and those are the coils. So we have let's say the water, the chilled water running through the coils to cool down the refrigerant or the air. So regardless, or as I've mentioned, it could be just simply a water piping system. So the pump is running the water through all these coils. So if we call them 1, 2, 3, 4, if you want, or I can call this pipe number 1, 2, 3, 4. But hold it for a second because we're going to have more details coming. So we need to find the pump requirements. So I need to find the maximum head needed by the pump and the flow rate, and that would be needed to find the power. But first we need to find the head. The flow rate seems to be slightly easier to find because we have the sections here and the refrigerant or the fluid in general flowing through each one. So the one that goes through the first coil, which is in line AH, it's 5 GPM. So here we have 5. GB, it's 4. CF, that's 9. And then the last one, DE, it's 7. I'm looking into the pump requirements, so I need to find the flow rate that the pump is delivering. So as you can see, those are in parallel. They have different values for the flow rate. You can combine them here, or you can combine them in the return line. So we have 5 plus 4 plus 9 plus 7. That would be 25 gallons per minute. And that would be the total flow rate that the pump is delivering. It would be 5 plus 4, and that's one of the characteristics for parallel systems. The flow rate is added, but not the head loss. Now, I'm going to just remove these. So don't jump into the assumption that the head loss at the first one equal to the head loss across DG equals to the head loss across CF equals to the head loss in DE. Actually, this is head loss, and these are pipes here, so we need also to consider these lines. So in fact, to solve this correctly, we have to look into the overall path. The only common, so if we go back to that example here, so pipe 1 was common for both 2 and 3, and that's why it was dropped. If you look here, this AB is not common for all because it doesn't exist here. It is common for this line, for the flow once it crosses. So the best way is to look into the path that the pump is supporting. So you have path number 1, and then path number 2, path number 3, and path number 4. So you have 4 paths that the pump delivers, it runs the flow through it, and it's coming. At the same time, it's running. Now we need to find the flow rate. We already found it, it's 25 GPM. That's how much the pump is delivering. But how much the head should be. So I need to find the maximum head that the pump is delivering, and that's why I need to consider paths. For example, that's path number 1 that goes through the first coil and it comes back to the pump. So I'm going to call this as path number 1. I need to find the head loss in this path. And then next, I will find the path number 2. So I'll start from the pump. I'll go all the way to here, go up through the second coil, and then come back. So this is gallons per minute. And then we will calculate also the head in the third branch, which has 2 coils now. So that's path number 3. So that's 3. This is 2. And then we have the last one, that's path number 4. It doesn't necessarily need to be the longest, it has the maximum head, because as you can see in this example, actually 3 has 2 coils, whereas the 4th one has only 1 coil. So maybe there's, it's okay here, yes, each coil has, all coils, they have the same head loss across them, but maybe sometimes you have head loss in some coils. Maybe some coils are larger than the others, or maybe just if you want to neglect coil, maybe that component has more pressure drop inside it. So before we start the calculation, so let's understand what's happening. Now the pump has to deliver the flow through path number 1, 2, 3, and 4 at the same time. However, we don't just come and add the head loss. It's just head loss, all these, and then I would multiply this by 5. No, that's like you're over designing your pump, because that's not needed. I need to know the maximum across each one. Of course, where would those be equal? That's the common line, and that's the common line from H to I back to J and then to the pump. Those are common for all 4 paths. So AH or ABGH or ABCFGH and so on, I need to find all these 4 and then use the maximum. Why? If the pump can, let's say number 2 was the max. So let's calculate it and then we can do the discussion. Or if number 2 had the maximum head, then the pump, that's the head that the pump should deliver. If this was 10, 40, 30, and 20, just some numbers, so that's the maximum, then the pump should have a head of 40 feet. Why? Because if it has 40, then it should be able to deliver this, which is only 10. It should be able to deliver through path number 3, which is 30, and it should be able to deliver through the 4th one, which is only 20. But if you consider the longest run, which is this one, I see it, then you're going to say the head of the pump is only 20. Well, it won't be able to deliver. The resistance is more than, the head loss is more than 20 in these 2 paths, and it won't be able to deliver. Okay? Okay, I have the second one. let's do path number 1. We'll try to compress things here. Write this on the next slide. All right, let's do the head loss in path number 1, through path number 1, as we did in the proof. All right, what do we have? We have from the pump to A, probably I have GA, yeah. So I have JA, that's all the way from here to here. So you can start from A. Let's start from point A, but keep in mind we're starting from A. So it's AB, from A to B, plus, actually no, path number 1 doesn't go there. We directly jump from A to H, plus a coil, the head loss in one coil only, and then I have HI. Of course, you could just, if you wanna make it easier on yourself, just calculate HI, IJ, JA, because it's going to be used in all these 4. But just to show the lines, it's AH, HI, plus IJ, plus J through A. I only do the first one, I'll show you the other ones, and then we'll look into the numbers. So the first one, AH, it's 8, plus 5, that's the head loss in feet, plus HI, 5, IJ is 8, plus JA, that's 6. So this should be 32, 16, 22, 32 feet. The second path, which is, let's keep the red code, so head loss 2. Alright, here we have A, B, and then we'll go from B to G. Again, that's the head loss. So that I'm just don't write head loss, BG, and so on. And then GH plus HIJA. If we, of course, don't forget the coil, we have one coil, and that would be 37 feet. And then we have number 3, head loss through path number 3. It's AB plus BC plus CF plus 2 coils, before we forget. And then we have the rest. And this would give me 47 feet. The last one, I'll just point it. So we have AB, BC, CD, and then DE, one coil, and then this EF, FG, GH, and then HIJ, and back to A. The difference was actually, the difference in one of the coil would take care of the additional head loss, in C, D, and EF. C, D, and EF, that's 5, and the additional coil in the third, it's 5. I'm saying this because head loss 4 would also give me 47 feet. Let's keep it in purple. Okay, so now the pump needs 32 to go to push the flow in pipe number 1, 37 in 2, 47 in both 3 and 4. So what should my pump head be? Here was 32, B 37, 47, and 47. Again, we have to take the max, not add them. You don't add the numbers together. No, I only need if you add it actually, or if you add all these numbers that you see here, it's going to be more than, I believe it would be like 100 something. But if the pump, that's the max, so the head for the pump has to be 47 feet. If you give it more, it's you don't need it. 47 should be able to push it through this, which needs only 32. Here, which only needs 37, and here 47, 47. Why? Because we just proved that the head loss in parallel system, it's equal. It's not the summation of the different systems together. Okay, so that's the first part of this question, the head of the pump. And then we need the power. We already calculated the flow rate for the pump, so that would be equal to 5 plus 4 plus 9 plus 7. That's equal to 25 GPM. Therefore, the hydraulic horsepower in HP, which is, we have this equation. Start it first, since I don't have the pressure in PSI. The head of the pump in feet, it's 3950 times the hydraulic horsepower divided by Q times the specific gravity. So it's the head of the pump, 47 feet into Q, 25 GPM. What's the specific gravity, do they say? It's 0.9 divided by 3,950, and that would be 0.27 horsepower. All right, thank you.